through this hands-on activity, where essentially they are recreating the key foundations of astronomy in terms of observational astronomy with their hands on a paper plate, we can in turn lead them to a better awareness and understanding of the stars through this hands-on type of activity with paper plates. And I really like that. I really like that concept.
Since the 15th century, round paper instruments called volvels have supported the teaching of astronomy. The inclusion of volvels in Peter Appianus's ambitious undertaking, Cosmographia, helped to propel the book to the 16th century equivalent of a bestseller, being printed in at least 45 editions in 4 languages. Paper plates were used to inspire creative thinking as early as the 1950s, when they allegedly inspired the blunt body design of the Mercury spacecraft. Since 1992, members of the Great Lakes Planetarium Association have developed a collection of paper plate activities that reduce complex notions to simple paper plate explanations. Dozens of inexpensive activities that support lessons in multiple disciplines for all ages are available at the Paper Plate Education website. This video will demonstrate the construction and use of 9 hands-on activities, mostly for advanced students but adaptable to all ages. These activities are interactive, they are inexpensive, they are instructional, and they are fun. So here is what we are serving on paper plates. Enjoy. We'll begin with sunrise, sunset. With this activity, you draw a local horizon around the perimeter of a plate. Over several months, track the changing position of the sunrise or sunset against the local background. With the satellite tracking bowl, you plot the predicted passes of satellites onto a bowl, which you can take outside as a viewing aid. The subsolar cup indicates in real time the position on the Earth at which an observer can see the sun directly overhead. This allows the user to track the changing position of the sun between the tropics and to trace out and define the analemma, that figure 8 shaped feature seen on some globes. The altitude measurer is an astrolabe-like device that allows you to measure in degrees the altitude of celestial objects up from the horizon. The Platisphere is a device that reduces the sphere of stars to a paper plate. With this tool, you can accurately determine the positions of the circumpolar stars for any given time and any given date. This video shows several variations of the Platisphere, including a children's version, a tactile version for visually impaired users, and the Photographic Plate, which predicts the smear of stars or star trails produced from a long-duration exposure on film. The Latitude by Polaris plate illustrates how navigators used the North Star to determine their position, correlating the observed altitude of Polaris with the person's latitude. The altitude of the noon sun plate demonstrates the range of the sun's altitude through the seasons for any given location. It also conveys why the sun sometimes never rises in the far north for months at a time. With the moon finder, you observe and plot the moon's phases and its position relative to the sun. Then you make a model which can predict the position of any given moon phase for any date and any time. Lastly, with the paper plate planet pointer, you plot the position of the planets in orbit around the sun and make a device to transfer that model to the real night sky. Essentially, your device shows you where to look to see the planets. So let's begin. Have you ever noticed when driving how the sun rises or sets to the side of an east-west road, but near the equinoxes it appears directly in your path? Here, you will observe and record the changing position of the sun at sunrise and sunset through the seasons. Imagining yourself to be at the center of the plate, you will mark the changing position of the sun against local landmarks. Around the perimeter of the plate, label the cardinal directions and draw familiar features: trees, houses, a flagpole. Then observe the sun for several months as it moves northward from its winter position through east until it stands still at its summer solstice limit. Then the sun appears to turn around and head back south along the horizon to its winter solstice extreme. In this farm scene example, the sun is shown here rising left or north of the silos in the summer. Between the silos, at the equinoxes, and right or south of the silos in the winter. With the satellite tracking bowl, you plot the predicted path of visible satellites on the inside dome of a bowl. Then you use the bowl as an alignment tool to face in the direction and anticipate the path of the satellite crossing overhead. Conveniently, foam bowls such as Hefty brand have 36 decorative scallops around the perimeter, so each scallop represents 10 degrees. You can calibrate your horizon into 360 degrees of azimuth, or you can label the cardinal points, north, south, east, and west, and draw features of your local horizon similar to the sunrise-sunset activity. Notice here who we have on the near edge, the 0 degree mark for north, and on the opposite side is south. One bowl you will cut in half to make a tool for plotting the satellite's positions onto a second bowl, which is the end product. Envision yourself standing under this bowl or dome of stars overhead. You want to mark the angular amount from the horizon, or 0 degrees, up to your zenith, overhead at 90 degrees. Hold a protractor against the edge of the halved bowl and mark 0 to 90 degrees near that edge. Then label those hash marks 0 through 90 degrees. Obtain satellite data for your location from the Heavens Above website. It lists satellite name, when the satellite pass starts, maximum altitude, and when satellite visibility ends. Here's an example of how you will plot the satellite position. Place the half bowl inside the whole one and rotate it so that the 0-degree mark is near the desired azimuth or compass heading. Then go up to the desired altitude and mark that spot on the bottom bowl. From this evening's predictions, we see the object named Meteor 129 rocket, magnitude 2.5, is first seen at this time 10 degrees of altitude in the south-southeast. Here's the southeast. So this is south-southeast. Place the bowl there. And make a mark at 10 degrees. Next, this satellite reaches a maximum altitude of 88 degrees toward the north-northeast, which is essentially overhead. You can plot this. Here's north-northeast and 88 degrees. The satellite pass ends at 10 degrees in the north-northwest, which you again plot. Notice how sometimes the full duration of the satellite pass cannot be seen due to obstructions nearby. Draw a line connecting these points. And label the path with satellite name and starting time when the satellite first appears. In this example, 1918 is 7:18 p.m. When you are done, you have an entire evening's worth of predicted passes represented visually on the bowl. To use it, you hold the bowl overhead. Align yourself in the proper direction and look near the predicted spot in the sky for that satellite. With the subsolar cup, you position yourself on top of a globe. Crosshairs on the cup indicate the location on the Earth, called the subsolar point, where the sun would be found directly overhead at that moment. Using an opaque plastic cup, on the bottom, dead center, drill a small hole. On the side, cut out a large viewing port, and on the front, affix these crosshairs, again so they cross dead center. On a sunny day, align your globe north and south. Your meridian and the globe's lines of longitude should be parallel. Concurrently, position it so your location is on the top of the globe. In this example, we are filming from Cleveland, Ohio, so a figure placed on Cleveland would be upright. To help align the globe accurately, place a bubble level on top, in this case Cleveland, and adjust it, still keeping the globe aligned north and south. To use the cup, you hold it over the globe so that the circle of sunlight is centered on the crosshairs. Here, on a mid-March morning, you see the subsolar point just off the coast of Brazil, near the mouth of the Amazon River. Later in the morning, you can see how the path of the sun has shifted westward into the interior of Brazil. This introduces other lessons in geography. Later, this mid-March afternoon, you can see the sun has moved over the Pacific Ocean, but is still just below the equator. So while you can record the sun's changing position from day to day, you can also record its changing position from week to week through the seasons. Here, after the vernal equinox, you find that the sun has moved north of the equator. As a variation, you can use a simple piece of pipe with crosshairs. Imagine it to be a water well and simulate the work of Eratosthenes, who used the observation that a well located on the Tropic of Cancer reflected the sun on the summer solstice. The well cast no shadow. This well defined the northern limit of the sun's path and led Eratosthenes to determine the circumference of the Earth. For this activity, we will make an astrolabe-like device for measuring in degrees the altitude of celestial objects up from the horizon. Using a foam plate with 36 scallops around the perimeter, mark and label 10-degree increments from 0 through 90. From the 90, draw a line across the diameter of the plate. Place a straight edge along the diameter and draw another line parallel to and above the diameter. As shown here, on the flat part of the plate, in from each edge, draw 2 perpendicular lines between the horizontal lines. Neatly cut across the plate along the upper line. Then cut in along the diameter as far as the short line you just drew. And repeat that on the other side. Score the perpendicular line from the horizon up to the top edge. And bend the tab back one way. Repeat that on the back side of the other edge of the plate and bend that tab back the opposite way. For clarity, we put red lines along the top of our viewing sights. From the center of the plate, midway along the diameter line, suspend a weight from string. When using the altitude measurer to sight a star, the plate cannot appear open. Rather, the sides of the plate are unseen and the 2 gun sights should be side by side. If the near gun sight is lower, then you are aiming too high. If the distant gun sight is lower, then you are aiming too low. They should align together with the target visible along the edge of the plate. Though the targeted celestial object shown here looks like the sun, you must never use this device to view the sun directly. Eye damage can result. Have a partner read the angular measurement off the front of the plate. A planisphere is a device that reduces the sphere of stars to a plane surface. Around the perimeter, you find dates and times for setting the dial. In this activity, we will make a platisphere, which reduces the circumpolar stars to a paper plate. With our device, you can determine the position of the circumpolar constellations for any given time or date as they rotate around Polaris. When you are facing north, as the hours pass, you see the stars move starwise or counterclockwise. If you denote north, due north, with a red meridian line, you see the pivot point around which they rotate is Polaris, the North Star. We will use some astronomy software to make a star chart for this activity. While centered on Polaris, set the sky to January 1 at midnight. Make the field of view equal to 50 degrees. And if you live with light pollution, set the limiting magnitude to 3.5. In addition to the red meridian, enable the constellation outline, then print out the star chart. Here is the red meridian line. Polaris is at 90 degrees of declination. Then there are 80, 70, 60, 50, and 40 degrees of declination. Cut out along the 40-degree circle of declination, being sure to include the major stars Capella, Vega, and Deneb. Center and affix the star chart on a stack of 9-inch black paper plates. We will use the following technique to mass produce plates for a large group. On an area where there are few stars, put a clamp over an entire stack of plates. At a drill press or with a hand drill, you will use 3 different sized drill bits. Use the smallest bit to drill through the fainter stars and a larger drill bit to drill through the brighter stars, as indicated on the star chart. The platisphere really works well when you limit the number of constellations depicted. You can always add them later as your observing progresses. Also, if you are in light polluted skies, omit the 4 fainter stars in the middle part of the Little Dipper. It's recommended that you do include the 3 bright guide stars, even if the printed star chart shows them to be below the horizon at the moment. With a large bit in the drill, move up along the north meridian line and drill a hole at the top of the plates near the edge. This will be what we call the indicator hole. When you remove the star chart, you have a stack of black starfield plates remaining. Here's the Big Dipper, which leads you to Polaris, and beyond to the W of Cassiopeia. Down low are Deneb, Vega, and up high is Capella. Now, to make a horizon for your latitude, cut off the semi-transparent horizon from the bottom of the printed star chart. Then center the truncated star chart on a larger 10-inch white plate and draw a line, onto the white plate as shown. Add a few horizon features, a house, a tree, and cut off the rest of the plate above that. To make individual horizons, put this horizon template on a plate, trace out the horizon line, and cut. To mass produce horizons, copy the template onto a stack of white 10-inch plates and cut the whole stack at a bandsaw or a scroll saw. You now have a black starfield plate, a 10-inch background plate with a small hole in its center, and a cutout horizon. Turn the horizon upside down and staple it to the big white plate, giving it a 3D appearance. Slip the black plate inside and secure them with a paper fastener. With the large indicator hole on top, set for January 1 at midnight, your Platisphere is ready for use. Beginning at January 1, every day the stars shift about 1 degree star-wise or counterclockwise. Until after 1 year, or just over 360 days, the stars have shifted through 360 degrees, hence the 1 degree per day. From January 1, we can subdivide the plate into 12 months. There's February 1, March 1, April 1, May 1. Keep spinning it around. October 1, November 1, December 1, and back to January 1, all being at midnight. Concurrently, every 24 hours, the stars will rotate about once around. So half a plate is 12 hours, a quarter plate is 6 hours. If we start on January 1 at midnight, a quarter turn takes us to 6 a.m., another quarter takes us to noon. Then here you see the hole on the right edge at 6 p.m., again all for January 1. And finally, by midnight, the hole has returned to about its starting point. We begin January 2. So let's try an example. Set the sky for April 1 at 9 p.m. From January 1 at midnight, move forward 3 months to February 1, March 1, and April 1 at midnight. Then set the time, moving forward 21 hours from midnight to noon. This is 6 p.m. plus 3 hours more to 9 p.m. So we'll move the indicator hole from the April 1 midnight position forward 21 hours to April 1 at 9 p.m. So this is how the stars will appear when facing north on April 1 at 9 p.m. Another way to get to April 1 at 9 p.m. From April 1 at midnight, you could go forward 21 hours. Or from April 1 at midnight, go backwards in time by 3 hours to 9 p.m. So again, this is how the north circumpolar stars appear on April 1 at 9 p.m. In the second example, you'll see how 2 different times and dates can have the same star field. From January 1 at midnight, move star-wise until the indicator hole is on the right edge, or at October 1 midnight. From here, you can move it forward either 2 hours or 1 month. This could be either October 1 at 2 a.m. or November 1 at midnight. Same star field, two different circumstances. Notice how at these two opportunities, the Big Dipper may be hard to find simply because it is low on the horizon and near obstructions. And since the end star of the Big Dipper, called Alkaid, dips below the horizon from this latitude, it is technically not a circumpolar star. Real quick here, to make a platosphere that holds up in the weather and has been field tested in the hot tub, make one out of two plastic plates. They fit together snugly, and the ridges help lock them together as well. You can modify the platosphere to simplify its use for children and adults alike. Instead of setting it for the exact time and date, you set it simply to a sketch of the current season and assume it is for evening use only. We'll use the same star field plates. From January 1 at midnight, back the star field up several hours, so this area next to Cassiopeia is upright, January 1 in the evening. Cut out a viewing window in that area. On a white background plate, draw figures to represent the four seasons. From winter on top, move star-wise to spring, summer, and fall. Be sure to draw them upright. Then place the black star field on top and secure with a paper fastener. In the winter evening, the Big Dipper stands on its handle. In the spring, the Dipper is seen high overhead, as it is in the summer. And in the fall, the Big Dipper is low. By winter, it returns to standing on its handle. The platosphere can also be modified as a tool for visually impaired students, as the following demonstration suggests.
Do today is to show you what a tactile map of what we call the circumpolar constellations would be like. And here you go. Show you how the slaves used the Big Dipper to find a way north for freedom, because they knew if they had wanted to escape, they had to escape to the north for freedom. What they did was they were taught to use these two stars in what I call the lip of the Dipper. Okay, here's the handle; those three make the handle, and these two are the lip of the Dipper. Okay, so here these three make the handle, right? And these four stars make the Dipper part, and these two stars are on the lip of the Dipper. Okay, if you draw an imaginary straight line through those two stars, it points to that star right in the middle of the plate. Okay, if you draw an imaginary straight line through those two stars, it points to that star right in the middle of the plate. And that star right there is what we call the North Star. Have you heard that? Polaris, the North Star. And if you put the hole over to your left, that would be a typical fall evening sky if the sun goes down. In the fall, where would be the Big Dipper? Where would you find the Big Dipper? About 9, 10 o'clock. See the Big Dipper maybe?
Maybe at the bottom.
Yeah. Down close to the ground, what we call the horizon, or at the bottom of the sky. How about Cassiopeia, the W, where would that be?
Almost up towards the top.
Yeah, be very high, up towards, or higher above Polaris.
To make a tactile platosphere, cut out the star field from a black plate and invert it. Center the upside down template on a red plate and drill your holes downward. Because the constellations appear backwards on the front of this plate, we use the red plate so as not to confuse it with the regular platispheres. It's been found that the back sides of the drill holes are more easily discerned by the fingers. If you take a long duration picture of the circumpolar stars, it produces a smear of stars called star trails. You can use the platisphere to make a photographic plate, which predicts the star trails for an exposure of any given duration. In this example, you can simulate the view of the heavens on the opening hours of the new millennium. Divide a 10-inch white plate into 24 hours. For our sample millennium photograph, we will take a 3-hour exposure. Set the platisphere to the starting time. Place a pen in the hole of a star and swing an arc through the 3 hours. Then back up to the starting point and do it again with the next star. Repeat this for every star hole. When you are done, remove the star field plate to reveal the photographic plate. And this is how the new millennium really began. Here we will show how a navigator determines her latitude from the altitude of Polaris, the North Star. As our navigator's ship travels from the equator, the altitude of Polaris above her horizon not only increases, but is congruent with her latitude. By the time she reaches 90 degrees of latitude, the altitude of Polaris is also 90 degrees. Draw a circle to represent the Earth on a 10-inch white plate. Extend the equator out to the edge and extend the North Pole out to the edge too. Label these the equator, celestial equator or CE, north, and Polaris at the north celestial pole. Polaris is so far away that its starlight is coming in parallel to the north celestial pole. Draw several parallel lines to reinforce this notion. Looking up any one of these lines of sight, no matter where you are on the Earth, will end on the North Star. With a protractor, measure and label the latitude shown here in increments of 15 degrees. From about this part of the Earth to about here, cut a slit along the perimeter of the Earth. Next, we'll use a 3x5 card, so mark it as shown here. We'll punch out a little hole here. And then draw some water with a ship on it. This is the direction our navigator would look toward the horizon. So label the arrow to horizon and highlight it. So this is the direction to our navigator's horizon, up from which she measures the altitude of the stars. Slip the card under the slit on the plate so the water line is on the edge of the Earth, with the vertical line visible at the Earth's center, right there. Mark the card underneath. Cut out around the ship and punch out the 2 holes as shown. On a second 3x5 card, draw a red arrow and label it north. Swing an arc. Punch a hole. And cut it out as shown. Fasten the arrow cutout to the ship cutout at the 90-degree bend. And then affix the whole rig to the plate. If our ship begins a journey north at the equator, the navigator looks this way to see starlight from Polaris coming in tangent to the equator. From the perspective of the ship, the direction of the North Star is straight ahead toward the northern horizon. The altitude of Polaris is 0 degrees. As the ship travels north, the angle between the horizon and Polaris, the altitude, becomes 30 degrees. At the same time, the angle from the ship's position to the equator, the latitude, is also 30 degrees. The ship moves north. When the altitude of Polaris is 45 degrees, the ship's latitude is also 45 degrees. By the time the ship reaches the North Pole, the pole star is directly overhead. Altitude equals 90 degrees. At the pole, the latitude is also 90 degrees. For a different perspective, you can focus in on the ship to see the angular height of Polaris rising congruent with angle of latitude. With this dial, you set the North Star to any latitude. You can then observe the range of the noon sun's altitude through the seasons at that location. Begin by drawing lines radiating outward from the center of a plate. Cut a wedge from another foam plate to expedite the process. Using foam plates with 36 scallops allows us to make 10-degree increments. You will place a house at the center of the plate later, with a line across the diameter representing the horizon. To the left is the northern horizon, to the right is the southern horizon. Label the plate 180 degrees from horizon to horizon, plus 30 degrees below each horizon, as follows. Start on the right edge and label upward from 0 degrees to 90 degrees. After 90, start decreasing back down to 0 degrees. Then, from the 0 degree marks on both edges, label 0 to 30 degrees below the plate's diameter. Draw a house at the center and cut out a slit along the ground and over the house as shown. On a second plate, you want to make a diagram similar to this. With the Earth at the center, you will project lines outward and label them accordingly. Then you plot the sun's position above and below the celestial equator for the 21st day of each month. This angular measurement from the equator is called declination, and it varies through the seasons. Draw a circle on a paper plate, and then place it on your foam plate. From the center of the Earth, draw and label lines. Equator, North Pole, with the North Star seen above it here. And if you extend the Earth's equator outward, it denotes the celestial equator. A line out to 23.5 degrees defines both the terrestrial and celestial Tropic of Cancer to the north and Tropic of Capricorn to the south. On the flat part of your plate, mark the position of the sun above and below the equator for the 21st day of every month. Notice how after June 21st, the sun's July 21st position essentially coincides with its May 21st position. Same for the pairs April and August, March and September, the equinoxes, February and October, January and November, and then the sun bottoms out on December 21st, the solstice, at 23.5 degrees. Drawing a line out through the June and December extremes again defines the tropics, which you can label. Cut off the crinkled edge of the plate, preserving your monthly suns. Slide this under your horizon plate and secure them with a paper fastener. Your device is now ready. From the previous activity, you learn that the altitude of Polaris above the horizon coincides with your latitude. So set the North Star to point to your latitude. If, for example, your latitude is 40 degrees, set the North Star line to 40 degrees. Then here would be the northern limit at the June solstice, and here the southern limit at the December solstice of the noon sun for that latitude. If you shift to a lower latitude, you can see how much higher the sun is through the seasons. Going to the latitude of the Arctic Circle, notice how the noon sun just touches the southern horizon on the December solstice. And going further to the North Pole, you can see how the noon sun remains below the horizon for 6 full months between the September equinox and the March equinox. With the moon finder, you first observe and record the moon's phases and its position relative to the sun. Then you make a model which can predict the position of a given moon phase for any date and at any time. Volvels are paper instruments that were often included in books. Here you see a 16th century volvel set to a waning crescent moon with the sun to its left. Your moon finder will be able to perform similar functions as that historic device. Envision a person facing south with her back to you. East is to her left, west is to her right. The noon sun is seen high in the south and then sets toward the western horizon. At sunset, it disappears below the horizon. But if the Earth were transparent, after sunset, we'd see it below the horizon. Using a paper plate, the setting sun looks like this. First, make a horizon plate as shown. And cut out the outer rim and the inner window. Draw a person with her back to you facing south. Again, east is toward the left horizon, and west is toward the right horizon. Color in some hair to reinforce that you and the figure are both facing south. The sun will serve as a time indicator, a timepiece of sorts, but refrain from calling it a clock. That only confuses people. In 24 hours, the sun appears to rotate around the observer once. At sunrise, the sun is easterly. At noon, it is high in the south. At sunset, it is westerly, and opposite of noon is midnight. Adding labels, when the sun is here, the time is PM. Down here, opposite the noon sun, is midnight. And when the sun is here, it is the AM. First, you want to observe the sun over time to see how far from the sun in degrees and in which direction the respective moon phases are seen. For example, one day from the afternoon sun, you may see the first quarter moon 90 degrees to the east. In the morning, 2 weeks later, the last quarter moon may be seen 90 degrees west of the sun, so record it there. Repeat these observations until you have most of the moon phases plotted on your plate. From a God's eye view above the Earth, with the sun shown off the plate in the distance, the half of the Earth opposite the sun will be in shadows, so darken in the night side of the Earth. Again, viewing from above the Earth's north pole, the moon will move this way around the Earth. Sunlight comes in from this direction, so when the moon is here, we color in the dark side of the moon and label it. This starting phase, where the moon is between the Earth and the sun, is called new moon. We'll bring the sun onto the plate, but imagine it at a vast distance. The moon then orbits this way 90 degrees. Color in the dark side and label it first quarter. The moon has traveled 1/4 of its orbit around the Earth. Another week later, when the sun and the moon are 180 degrees opposite from each other, we have a full moon. So we'll color in the dark side of the moon, again, seen from above. After 3/4 of its orbit, the moon reaches the third quarter or last quarter phase.